Okay, this lesson is on solving exponential equations. As we near the end of Unit 7, we start to actually get to solve some equations. We're going to start with solving exponential equations today, and the next lesson will be on solving logarithmic equations. And so we're actually going to get to solve these. So a couple ways that we can solve exponential equations. And one is sort of the easy way. If it works out, then it's the easy way. And the second one is for the slightly more complicated problems. The first way we're going to talk about with solving exponential equations is using the property of equality. Okay, the property of equality is a really you might think it might be obvious, but it's one of the things that is pretty cool if you can get it to work out because it makes things a lot easier. So, what is the property of equality? Basically, the property of equality of exponential equations states that if you have the same base of an exponential equal to like the same base of another exponential, so b to the x equals b to the y, so I have an equation set where both sides have the exact same base, then x just equals y. It turns out that if they have the same base, that the we can get into the property of logs and stuff like that, but basically if they have the same base, then it simply is just the exponents set equal to each other. So for example, if I had 3 to the x equals 3 to the fifth, then it's just simply then x just equals 5. You just set the exponents equal to each other. So this is pretty cool. If it works out, then it makes this pretty quick. So let's look at some actual examples. So if we look at the first example, notice that the bases are the same. They both have a base of, and let me do that a little bit better. There you go. They both have a base of 4. So it is simply just 2 equals x minus 5. And then you would just solve that equation. So you would add the 5, and you would get 7 equals x, or x equals 7. That one's obviously pretty straightforward, pretty easy. But, sometimes even if the bases aren't the same, that you can manipulate it in a way that they are. If you know that the base on the left-hand side is 2, and the base on the right side is 4, well, you might think at first that the bases are not the same, so we can't do this. But we can make 4 is, I mean, there's another way to get 4, and you're probably already thinking about it. But 4 is just 2 squared. So I can write it like that. I can just put this in place of that, and I end up with 2 to the x equals 2 squared. Now that 2 is going to go up top with the 2x plus 1 and multiply it. Now you don't need to worry about that right now, but now we have the bases that are the same, and so we can just set the exponents equal to each other. So it's just simply x equals, the one exponent equal to the other exponent. And now we can solve that, and x equals 4x plus 2. Let me slide down here. More room. Subtract the 4x, negative 3x equals 2. Divide by negative 3. I think you guys can figure it out from here. And x would equal negative 2/3. So that's one way of doing it through the property of equality. And we'll do a couple more here just to show you. I'm not going to solve the rest of these. I think you can solve an equation once you get it there. But just to get it, to where it is at this point to here, to where you've gotten the bases the same, and then you just set the exponents equal to each other, and for the rest of that, I feel like you can probably do on your own. So here's another example where you have a base of 2, oops, wrong thing, take the highlighter, base of 2 and a base that's not 2, but it is some form of 2. So just like the previous problem, which was 4, it is a factor of 2. So 8 is actually 2 to the third. So if I replace that, I have 2 times 2 to the 2x plus 1 power, and then 2 to the third times 3x power. Now that the bases are the same, we can set the exponents equal to each other. And so that's 2x plus 1 equals 3 times 3x, which is 9x. 2x plus 1 equals 9x. And then I'll let you solve it from there, because that should be pretty self-explanatory once you get to that point. So the other type of property of equality is, so it looks like this, where you have multiple things, and you just have to remember your rules of exponents. So when I'm multiplying two things, so we have e and an e, they're both the same base. Remember, when you're multiplying things that have the same base, what do you do with your exponents? Well, you add them. When you're multiplying things with the same base, you add your exponents. So 3x plus 2x is 5x. So I have e to the 5x equals e to the 25th. And now I have two sides where the exponents have the same base, e and e. So I can simply just set one exponent equal to the other exponent and solve. This one's pretty easy, so I'll just finish it. X equals 5. Again, pretty straightforward. So that is the property of equality. So when you have, and let's sort of zoom out here so we can see this. So when you have equations where they have the same base of the exponents, you can set the exponents to each other. Now, what happens if you can't do that? Like if it were a base of 4 and a base of 7, you can't really do that. So when it doesn't work out and you can't do that, you have to use logarithms, and that's what we've sort of been leading up to this entire time. So when solving exponential equations using logarithms, whether they're common or natural logs, there's just a couple steps. Step 1, you need to isolate the exponent, or the base and its exponent. Isolate base and exponent. If necessary, sometimes it's already isolated, but if it's not, then you'll need to isolate the base and the exponent. You want to get the base and its exponent all by itself. Sort of how you get x by itself, or when we were talking about radicals, you had to get the radical by itself. The same thing. So we need to isolate the base and its exponent. You're then going to take the log, or natural log, that's an R, or natural log, that's not an R, natural log of both sides. So, and remember that logs and exponents are inverses of each other, they're opposites of each other, which is why when you have addition, you subtract, and you have division, you multiply, and when you have a square root, you square. When you have an exponent, the opposite of something with an exponent is a log, and so when you have things with exponents, you're going to log both sides, and that will allow you to pull the exponent down using the power property. We just talked about properties last class. So you're going to apply power property, and we'll show you all these. The power property is where you can take the exponent and move it down and out front of the log, which will allow you to eventually solve the equation. So let's look at this. We'll start off pretty easy. So in this example here, the exponent is already isolated. So the whole point is to get this exponent isolated. So what we do once the exponent is isolated, we're going to log both sides. So I'm going to log this side and then log this side. That's a G. What that allows me to do is use the power property and take this exponent and move it out front, giving me x times the log of 2, that's a G, equals the log of 5. And you just simply solve for x. So to get x by itself, and I'll sort of highlight it, so we're solving for x, since that's multiplication, I can just divide both sides, and that is not a pen. There we go. Just divide both sides by log 2. That'll cancel, and then x will just simply be the log of 5 divided by the log of 2. And this is where you'll have to take your calculator out. So I'll do this here. Log of 5 divided by log of 2 is approximately 2.32. Well, if you go 3 decimal places, let's go 3 decimal places, so it'll be 3.22. It's approximately 3.2, oh Jesus, I'm all messed up. Let's try this again. It's not even 3. How about 2.322? There we go. So, that is all the steps right there. Step 1, isolate the exponent. Well, it was already isolated, so I didn't need to do that. Once it is isolated, then you logged both sides. So I logged the left, logged the right. That allowed me to take the exponent. Using the power property, which we talked about, you can move the exponent out in front, giving me x times the log of 2 equals the log of 5. Then just simply divide the log of 2 over to the other side to solve for x. And that's essentially what you're going to be doing every single time. So let's look at another example. Here, once again, the exponent is isolated. It's already by itself. I don't have anything extra over here. It's the base and its exponent. So I'm going to apply a log to both sides. So log this side, log that side. That will allow me to take the exponent and move it out front, giving me 9x times the log of 7 equals the log of 15. And just like before, we're solving for x. So we're going to divide, and let me change colors here. We're going to divide log 7 over to the other side. That'll cancel out, giving me 9x equals, I'll do log of 15 divided by log of 7 is 1.39. We'll do 3 decimal places, 1.392. And then just divide both sides by 9. Let's cross that out. So what I get is x equals, divide that by 9, 0.155. 0.155. Pretty self-explanatory. I mean, once you get the hang of it, it isn't anything that's too terribly difficult. So here's another problem where we need in this particular problem, we need to actually isolate the exponent this time. So remember, we need to get the base and its exponent all by itself. So the first thing we actually need to do is actually move the 1 over to the other side. By subtracting 1, I get 5 to the x power equals 359. Now that the variable, or the base and the exponent are isolated, I can apply a log. Oops, that didn't work. Log to both sides, log to that side. That will allow me to take the exponent and move it out front, giving me x times the log of 5 equals the log of 359. I will then just divide the log of 5 over to the other side. Sorry for my terrible handwriting. I don't have my stylus today. So x will just simply be the log of 359 divided by the log of 5. That is 3.65656. Pretty straightforward. Let's try just a couple more here. Okay. So let's look here. We're just going to do a couple more, and you see we got a couple base E ones, so I want to do those too. This is as complicated as this is going to get. Absolutely, this is as complicated as it's going to get, and you're going to see that it's actually not that bad. Again, the step is going to be to get your base and your exponent all by itself. Everything else will have to go, and so you're just sort of like solving an equation here. I'm going to add 18 to the other side. So I have 1/4 3 to the negative x equals 36. Multiply both sides by 4 to get rid of this fraction. So I have 3 to the negative x equals, that's about 144. Now the base and the exponent are isolated. I can then apply the log. So I will log this side, log that side. That will allow me to take the exponent, bring it out front, so it's negative x times, and I'll try to make that times a little bit better, log of 3 equals log of 144. And just like in previous problems, we're going to divide, oh my gosh, log of 3. So it gives me negative x equals log of 144 divided by log of 3 is 4.524. And then I just have to divide both sides by negative 1, negative 1, negative 1. That just switches the signs. Let me go over here since I have room over here. X will then equal negative 4.524. And that's it. So a couple more here we want to do just to show you that they can come in base E. So you'll have to use the other log here. So here we have a base E exponential, but it doesn't change the process. You're still going to try to get the base and the exponent by itself. Be careful not to assume that the 3 is with the base. There's only one thing that's under the exponent, and that one thing, unless you see parentheses, it's only the one thing that's under the exponent that is what you're isolating. So I'm going to add 14 to the other side. So I have 3e to the x equals 25. And then we're going to divide by 3, divide by 3. This is going to give us, definitely it's going to give us a decimal. So e to the x equals 25 divided by 3 is actually 8.333333. Now, to be as accurate as possible, you're going to want to leave that in your calculator. So don't clear that out or round. To be as accurate as possible, I'm going to leave the 8.333 in my calculator, because the next step here is to apply the log to both sides. Now, because this is a base E exponential, we have to use the natural log, and that's very important. You use a regular log, it's a different value. So when you have a base E, you have to use the natural log of both sides, the natural log. That will allow this to move out front. And then you have x times the natural log of e equals the natural log, and that's, there you go, natural log of 8.333. Now, a couple things you could do. If you didn't recognize this, you could just divide both sides by the natural log of e. But what you should be able to do by now is recognize these sort of things. And what we have, natural log of e, remember that the base of a natural log is e. And so I have the natural log base e of e. So essentially, that just cancels out. You know, if you didn't recognize that, though, you could just divide both sides by the natural log of e. You would have gotten the same answer. So what I have is just whatever the natural log of that. Now, keep in mind, I already kept this in my calculator. So I'm going to do natural log. And if you hit second and your negative button, it's down by the decimal point. Second and the negative button, it'll put the it says ANS. That's your previous answer in there. And then you can hit it, and it will use your previous answer in the problem. And so you end up with 2.120 as the answer. Okay, one more. I feel like we should maybe just do one more here, and just to get a little bit more practice. So again, this is another one where we have a base e, and we do need to isolate that base. So I'm going to add 7. That'll give me 4. E to the negative 0.3x equals 20. Divide by 4, divide by 4. E to the negative 0.3x equals, I don't know why I drew the equal signs way up there, equals 5. And now that the exponent is isolated, and we're dealing with a base e exponential, I have to use the natural log. Natural log. This will allow me to bring this out front. So it's negative 0.3x times the natural log of e. But if you're paying attention to the previous problem, actually just cancels out. And I just have the natural log of 5 on the other side, which I'll actually just calculate now. Natural log of 5. This is approximately 1.609. Again, I'm going to keep that in my calculator so I can have exact values here. So I have as negative 0.3x equals 1.609 divided by negative 0.3 divided by negative 0.3. I already have this kept in my calculator, so if I just hit divided by negative 0.3, it'll give me an exact answer, well, close to exact. X equals negative 5.365. That is a 5. There you go. And so that's the other way of solving logs. So we have the property of equality. If the bases are the same or pretty close to the same, you can use the property of equality to just set the exponents equal to each other. But in most cases, you're going to have to do this. You're going to have to, you're going to have to use logs. So, and it's no different. You know, we're going to do a word problem here, again with decay, to show you how you can actually solve these. Now, before, we actually had to do this graphically. We had to put the left side into y1 and the right side into y2 and somehow search for the intersection point. And if I didn't point you to the right direction, you'd probably be searching forever. So logs are definitely the quicker way of doing this rather than using your graphing calculator to find them on a graph. So you have a certain element that decays according to the formula P equals P sub 0 e to the negative 0.12 t, where t is in years. So real quick note about exponential decay. You might see this P sub 0. Let me highlight it. This P sub 0 here. All that means is that this is, think of P sub O. This is the original. So whatever the original amount is, that's what would go there. And then P is the actual amount. So Oftentimes, you're asked to calculate half-life, and this you may have done this in a chemistry class, but a half-life is a pretty common calculation in terms of decay and elements and stuff like that. And so, how long will it take this particular element to decay to 1/2 of its original amount? Now, it doesn't give you the original amount, so you have to think, okay, well, half of its original amount, I don't have the original amount. If it doesn't give you the original amount, so like you notice here, so it says decay to the 1/2 of its original amount, but we don't know its original amount, just make it up. So just make up a starting anything. It's real easy to just use 10 as the original, because you can always do half or a fourth or a third or whatever of to do 10. It's just an easy number. You could use 100 too, any number, but just make it up. So if my original, I can just make it up, is 10 e to the negative 0.12 t, and half of its original amount, well, then it's going to be half of 10, which is going to be 5. I can do this and actually calculate and solve for t using logs. So just like in the previous problems, we need to get the exponent and its base isolated. So and that didn't really work out. There we go. Let's try that again. There's our base and our exponent. We need to get those isolated. So I am going to divide both sides by 10. So, and some of you guys might recognize this pattern pretty early on, but you'll always have on the left-hand side whatever you were trying to find in the original amount. So because it said half, notice how this over here on the left-hand side is 0.5. And that'll be true with anything. So if it said a fourth, it'd be 0.25 and so on. So, and then you have e to the negative 0.12 t. Now, to solve this, we have a base e. We're going to use the natural log of both sides. So that allows this to move out front. And so let me just slide over, didn't really work, slide over to the right here and do this. So I'll have the natural log of 5 equals negative 0.12 t times the natural log of e. Again, natural log of e cancels out, makes it pretty easy, and so all I have to do to solve for t is divide by negative 0.12. Divide by negative 0.12. So t will equal the natural log of 5 divided by negative 0.12. And so it looks like, and we have, let me go back there. I knew that didn't look right. I forgot that it's the natural log of 0.5. There we go. And so when you do the natural log of 0.5 divided by negative 0.12, this answer should make a little more sense. And it does, yes. So we end up with t equaling 5.776 years, since time was in years. So that means that this particular element would decay to half of its original amount after 5.776 years. So the next part of this just simply says, well, how long will it take for the element to decay to 1/4 of its original amount? If you already understood this whole thing here, so whether you start with 10 and end up with 5 because it's half, or 100 and this is 50, or 60 and this is 30, or 10, or 20 and this is 10, it's always going to end up as 0.5 because it asked for what is half of its original amount. So you can use the same sort of knowledge and understand that if it's going to decay to 1/4 of its original amount, it'll just be simply 0.25 equals e to the negative 0.12 t. And so, and in any amount, you could do any amount. 1/5 and it'd be 0.2. It doesn't matter. And so all we need to do is then take the natural log of both sides. And so I'm left with the natural log of 0.25 equals negative 0.12t times the natural log of e, which will cancel out. And then to solve for t, I just divide by negative 0.12 again. Divide by negative 0.12. And so I have the natural log of 0.25 divided by negative 0.12. And I get 11, so t equals 11.552 years. So that's it. That's logs, that's exponential, it's solving exponential equations with logs. Thanks. Let me know if you have any questions.